Hello students, in this video we'll discuss the canonical form of a curve near a point. Let's be given a curve in arc length parameter. And assume that gamma of 0 is just the 0 vector. In other words, I'm going to center this curve is going to start at the origin, right? So in other words, here's the x, y, and z axis. And the curve is going to start over here, right? So that's where my curve starts. And then what I can do is I can Taylor expand the curve at the origin, right? So let's do the Taylor expansion. So Taylor expand gamma. Near the origin. Okay. So it says that gamma of s is the sum, n goes from 0 to infinity, of gamma n 0 over n factorial s to the power n. Okay, easy enough. And so I'm going to write out the first couple terms in this expansion over here. So gamma of s is equal to gamma of 0 plus s gamma prime of 0 plus s squared over 2 factorial gamma double prime of 0 plus s cubed over 3 factorial gamma triple prime of 0. Now I know that gamma prime, gamma double prime, gamma triple prime give me everything I need to know essentially up to the curvature at that point and the torsion at that point, right? On a plus the higher order terms over here, right? So we're going to look at this locally as a cubic approximation. Good. Now we can simplify this over here because we know gamma of 0 is equal to 0. Now let's compute this expression, and this expression over here. So what's gamma prime of s? So gamma prime of s is going to be what? Gamma prime of s is just d by ds. d by ds of gamma of s, which is just t hat of s. And so gamma prime of 0 is just the tangent vector at 0. So gamma prime of 0 is just the unit tangent vector at 0. And then gamma double prime of s is just d by ds of the unit tangent vector, which of course we know by Frenet-Serret number 1, by Frenet-Serret number 1. This is going to be the curvature of s, and then in the direction of the principal normal vector, right? So it says that gamma double prime of 0 is going to be what? Is going to be the curvature at 0, p hat of 0. Beautiful. And then finally was gamma triple prime. So gamma triple prime, this is where it gets interesting, right? As we saw from our previous study of curves, this is where it gets fun. It's going to be the derivative of this expression over here. So it's going to be kappa prime of s, p hat of s, plus kappa of s, d by ds of p hat of s. Okay. And of course, by Frenet-Serret number 2, this is going to be kappa prime of s, p of s, then plus negative curvature of s, t hat of s, plus torsion of s, b hat of s. So that's the hardest one. So let's write that. Let's summarize that. So my summary tells me this. Tells me that gamma triple prime. So this allows me to write that gamma triple prime of 0 is going to be what? It's going to be kappa prime 0, p 0, kappa prime 0, p hat 0, plus what? Plus torsion of 0, b hat of 0, and then finally minus curvature of 0, t hat of 0. So that it contains all three of them, right, in this gamma triple prime, right? Gamma triple prime of 0. And so now what I want to do is I want to basically arrange these things so I can apply a rigid motion to the curve. So apply a rotation to the curve such that t hat of 0 goes to I hat, p hat of 0 goes to j hat, and b hat of 0 goes to k hat. Okay? I know that T, P, and B, so TPB is the Frenet-Serret frame. And there's mutually orthogonal vectors, right? So they're mutually perpendicular. Since they're mutually perpendicular, I know I can find a rotation which does this, which takes TP and B, which may look like this, and just put them into IJK coordinates, right? So in other words, right here you have your t hat of 0. Over here you have your p hat of 0, and then over here you have your b hat of 0. So now my curve is in this frame, okay? So in other words, we know what the normal osculating and rectifying planes are in this case. They're just the xy, yz, and zx plane. Okay, beautiful. And so now what I'm going to do is I'm going to write down this expression over here. So now what's my gamma of s? Well, it's going to be s t hat of 0, so it's going to be an si hat, right? That's from over there. That's my si hat. And then I'm going to have a kappa 0, so plus kappa, the curvature at 0, whatever the curvature happens to be there. P hat of 0, which is going to be a j hat. And that's in what? That's in the direct, that's my gamma double prime of 0 times s squared over 2 factorial, s squared over 2 factorial. Good. Plus s cubed over 3 factorial, s cubed over 3 factorial. And then this whole expression over here. So that's going to be kappa prime of 0, and then j hat, and then plus torsion of 0, k hat, and then minus curvature of 0, t hat, which is going to be an I, right? Good. So now let's gather the terms over here. So what's this going to look like? It's going to look like s has an I. There's no I over here. There's an I over here with a negative kappa of 0 over here, right? So negative kappa 0 times s cubed over 3, negative kappa of 0 over 3 s cubed. Those are my I components over here. What are my j components? Well, I'm going to have a kappa 0, so I have a kappa 0 over 2 s squared. And then there's also this negative, then this plus s cubed over 3 times what? Times 3 factorial, of course, right? That's a 3 factorial. Good. Times torsion of 0. That's my j hat component. And then what's my k hat component going to be? My k hat component is right over, oh, I'm sorry, that's not torsion, that's the k hat component. So let's correct that. So what is this going to be? So the j hat component over here, we got that j hat component correct, and then the j hat component over here is going to be kappa prime of 0 over 3 factorial s cubed, like that. That's the other j component. And then finally, the only k component is this torsion term over here, right? So it's going to be torsion of 0 s cubed over 3 factorial, and that's the k hat component. Now, I can do one further, plus, of course, higher order terms, right? So in other words, it's approximately equal to this. This is an approximation of my curve, approximation, right? Now, if I do one further approximation, what do we see? If I do one further approximation, this is approximately, keeping the lowest order term we see, it's approximately s I hat plus kappa 0 over 2, kappa of 0 over 2, s squared j hat. And then over here, we'll have a tau 0 plus torsion of 0 over 3 factorial s cubed k hat. And we have a curve that looks like s squared, s cubed. We've encountered this curve in the past. This is just a twisted cubic curve over here. And we know what twisted curve or cubic is looking for. So the local approximation is that this curve over here has the structure locally of a twisted cubic over here, twisted cubic. So the Frenet-Serret together with the Taylor expansion shows me that at least close enough to a point, if I have the proper rotation, the curve always looks like a curve with non-zero torsion and non-zero curvature, always has the structure of a locally approximable by a twisted cubic. Thank you very much.